Alright, what we're looking here is spring question 2. This is the usual setup. We've got the spring unextended. This is where it would sit, the middle position, if it was just hanging there. At that point, mg equals kx. This is where it would bounce to if we dropped it from the unextended position. And I think we showed the forces there in the spring forces video. If you haven't seen it, you can go and have a look. So what I'm asking you for, though, is the velocity at that midpoint if it's doing full oscillations. So velocity at midpoint with full oscillations. And I want that in terms of g and x. So a way of looking at this is to think about the energy. Now the energy in the middle, you can define your potential energy anywhere. So I think I'll start by defining the potential energy at this point in the middle at 0. Wouldn't really matter. We could define it from the bottom. This is the second time I've done this video. I did it a different way last time. I think this way is going to be simpler. But if the potential energy at the middle is that point, then the only energy it's got, if it's just sitting there, is 1/2 kx squared, right? That's the elastic energy because it's got no potential energy because we just defined it there at 0. So what we've got to do with these problems, and this is the critical point, there's always a critical point in your thinking, is how do we think about how to set this up? And the way I think about it is, how would we make this oscillate? And how would that be different from the situation when it's just sitting there? Okay, so because when it's oscillating, when it passes through the middle, it still has that elastic energy. It's just that it's got a whole bunch more kinetic energy, and I think you realize that. But you could make it oscillate that by starting it from the top or from starting it from the bottom. So you then got to ask yourself, what's different about those situations? All right. Now the critical point here is that if you start it from the top or you start it from the bottom, then that energy that you've got in the system, if you start it from the top or start it from the bottom, isn't going to change. So that's your total energy. So when you pass through this midpoint, if you subtract off what it's got when it's not bouncing, you'll be left with what it's got when it is bouncing, kinetic energy. So the other video I did, I started at the bottom, and I felt like it was a bit more confusing to do it that way. It gave exactly the same answer, and afterwards you could do that if you want, after you've seen this one. But we'll start it from the top there. What's the total energy it's got there? Well, no elastic, no kinetic, just potential. So at the top, it's just got mgx, because I've defined h equals 0 there. Like I said, it wouldn't matter, but I've defined it there. So that's the total energy in the system. We've said in the middle, the total energy must be the same, but now it's, well, part of it's this elastic potential energy. So whatever's left over must be the kinetic energy. So we can say mgx minus 1/2 kx squared must equal 1/2 mv squared. That was it. That was the tough part done. Figuring that out, that the total energy at the top must be the total energy in the middle, and therefore whatever's left over must be the kinetic. Now we can go and solve this. Of course, we've got to do a few substitutions. So mgx minus 1/2 k, which is mg over x, x squared equals 1/2 mv squared. Cancel out that one, cancel out that one. We can cancel out the m's, and let's see where we're left with. Well, we can multiply everything by 2. Do we need to do that? Gx minus 1/2 gx equals 1/2. So we'll just multiply everything by 2. I think that will help. So you've got 2gx minus gx equals v squared. So we've got gx equals v squared, v equals square root of gx. And we're done. Easy.